Welcome to the hangar, rookie. Glad you made it. Look, today isn't just another day of shadowing. Today is your high-stakes pre-work review for your DGCA Car 66 technical exam. I've been on this hangar floor for longer than I can remember, and I have seen exactly what happens when AME students don't take tube fabrication seriously. We're dealing with the literal veins and arteries of the aircraft here. Hydraulic lines, fuel lines, oxygen. If you mess up, the bird doesn't fly right, or worse, it doesn't stay in the sky. So consider me your senior mentor today, and consider this explainer your ultimate survival guide. All right, let's dive right in.
Here's our pre-flight checklist for today. First, our welcome to the hangar. Then we'll cover precision cutting and deburring, bending and internal integrity, tooling and flaring mechanics, the visual inspection defect checklist, and finally, a final exam knowledge check. Let's get right to it.
Okay, moving into Section 2, precision cutting and deburring.
When you're making these precision cuts, you basically have two distinct paths. You've got the precision tube cutter, right? This is absolutely your go-to for soft metals like aluminum or copper. It gives you this incredibly accurate square cut with minimal distortion. Well, as long as you remember to tighten it gradually after each revolution. But, sometimes you're dealing with hard metals, like corrosion-resistant steel or titanium. That is when you need to grab the manual 32 teeth per inch hacksaw. Now, I gotta warn you, using a hacksaw requires intense precision. Sure, it decreases work hardening, but if you don't clamp that tube perfectly, the vibration damage is gonna ruin your piece, and you will literally spend forever filing it back to square.
Okay, so once you cut that tube, welcome to the deburring phase. Think of it kind of like a high-stakes minigame. You're going to have sharp metal burrs left on both the inside and the outside, and if you leave those sharp edges behind, man, that's an instant failure. Those burrs cause major system turbulence, they initiate cracks under pressure, and worse, they can shed catastrophic metal shavings right into the system. You absolutely have to get in there and remove them using a reamer or a fine file.
Listen, this right here is my golden rule of deburring. Never, ever reduce the wall thickness, or you will initiate a crack. Seriously, when you're cleaning up those burrs, you have to be surgical. Even microscopic damage, or just the slightest reduction to the wall thickness at the end of the tube, it leads to defective flares. And a defective flare, that means a massive boss-level fluid leak once the system is under pressure. Protect the tube's wall thickness at all costs, rookie. All right, Section 3, bending and internal integrity.
Now, smaller, softer tubes, you can usually just bend those by hand. But larger tubes, they require serious tools. And sometimes, standard manual benders just aren't going to cut it. That's when we use a little bit of hanger alchemy. We use alternative fillers to provide internal support, so the tube doesn't just flatten out and collapse when you try to bend it. So step 1, you pack the tube completely tight with fine, dry sand or a specialized fusible alloy. Step 2, you perform your bend really slowly over a forming block. And step 3, this is where the magic happens. If you use the alloy, you actually melt it right out under hot water at exactly 160 degrees Fahrenheit.
But, that brings us to a pretty critical survival question. If you just packed a tube full of sand or melted metal, how do you mathematically, visually guarantee that the inside is perfectly clean before you go and install it on a multi-million-dollar aircraft?
Well, the answer is the borescope. This is your ultimate verification tool. Honestly, visual internal inspection is literally the only way to prove that zero filler particles remain inside. Think about it. If even one tiny grain of sand or a single drop of alloy gets left behind, it's going to travel straight into the hydraulic or fuel system. It'll contaminate the valves, and it can cause complete mechanical failure mid-flight. We don't guess in this hangar. We verify with the borescope.
Next up, Section 4, tooling and flaring mechanics.
Okay, so when you step up to the bench to flare a tube, you really have to choose your tooling loadout wisely. And that choice is based entirely on the hardness of the metal you're working with. Trust me, ignoring material compatibility is the fastest possible way to fail your exam and get yourself kicked out of the hangar.
So, the absolute crucial point here is understanding these strict rules. Rolling type tools, they are strictly limited to soft metals. I'm talking aluminum, copper, brass. You are explicitly prohibited from using a rolling type tool on hard metals. Just don't do it. If you're handed a piece of corrosion-resistant steel or titanium, you must switch over to an impact-type tool or use heavy-duty CNC production benders. Never ever mix these up.
Let's actually break down the exact
physical self-gauging procedure for using a rolling-type tool on soft metals. First, you clamp the tubing so it's exactly flush with the top of the die block. Second, you move the yoke down over the die holder and lock it firmly into position. And third, you turn the feed screw down until a slight resistance is felt. That resistance is literally the tool telling you, hey, the flare is complete. Absolutely do not over-tighten it.
And why are we being so obsessive about this procedure? Because of one specific measurement, 35 to 37 degrees. That is the absolute non-negotiable aviation manufacturer specification for a flare angle. If you go to a local hardware store and buy an automotive flaring tool, it's going to cut a 45-degree angle. That is strictly forbidden in aircraft maintenance. A 45-degree flare will never seat right, it will leak, and honestly, it's a fatal error. Always verify your tool makes a 35 to 37-degree flare.
All right, moving on to Section 5, the Visual Inspection Defect Checklist. Before any fabricated tube even gets close to being installed on an aircraft, you have to hunt down a few specific enemies. I'm talking about wrinkles, which usually happen when you try to bend thin-walled tubing without a proper bending tool, sharp kinks from incorrect bends, cracks caused by applying excessive force with a tube cutter, or maybe just ignoring work hardening. Any of these pop up, and that tube goes straight into the scrap bin.
I really need to drill this specific external defect checklist into your head right now, especially the rule on flattened sections. See, a small amount of flattening during a bend is actually completely acceptable, but, and this is a massive but, that flattened portion must never drop below 75% of the original outside diameter. If you measure it and verify a flattened section is sitting at 74%, you reject it immediately. Ignoring the 75% spec triggers an instant fatigue failure the second that system gets pressurized.
And finally, Section 6, the final exam knowledge check.
All right, rookie, you've walked the floor, you know the tools, you've got the specs down, it's time for the boss battle. Imagine this is a real DGCA Car 66 exam question sitting in front of you. What is the main purpose of deburring an aircraft tube? Is it A, to increase tube weight? B, to prevent system contamination, or C, to reduce overall tube length? Well, if you remember our minigame from earlier, the correct answer is obviously B. We deburr to get rid of those sharp edges that cause fluid turbulence and shed catastrophic metal shavings into the system. You're doing it to protect the entire aircraft from contamination. To really lock this into your memory before you hit the hangar floor, here is the ultimate flawless fabrication combo. Ready? First, measure and cut with a precision tool, always cutting about 10% longer to absorb any bending variations. Next, deburr the inside and outside, being super careful to save that wall thickness. Then, bend it using the correct radius, making sure the flat spot stays above 75% of the original outside diameter. And finally, flare the tube to exactly 35 to 37 degrees. You hit this combo perfectly, and you guarantee maximum flight safety.
I'm going to leave you with this final thought. If a single microscopic defect, like we're talking a tiny scratch on the flare, one single burr left behind, or a bend that flattened out to 72%, if that goes unnoticed by you on the hangar floor today, how many flight hours do you think it'll be before the invisible ticking clock of that botched fabrication brings down the entire aircraft? The stakes in aviation maintenance are absolutely unforgiving. Respect the limits, respect your tools, and you are going to do just fine on that exam. Good luck out there.